Good afternoon. Today we are going to start looking into trees, and in particular, binary search trees. So let's begin first with some definitions and concepts which should be already known or at least have been seen before, but anything that you need I will introduce from scratch. So when I speak of a graph, or when we speak of a graph in general, we usually don't mean the XY coordinate graph like you plot a function. What we really mean is a collection of nodes and links connecting them. Okay? And that's just a very abstract conceptual idea. If you want to think of a linked list is a graph where you've got each node has either one or two neighbors on its left or right. Okay, so it's literally just a collection of nodes or a collection of data that is connected to a nearest neighbor. And in general, a graph can have multiple connections. It could even connect to itself. It could even have multiple edges between 1 and 5. And the world, the Facebook graph, you may have heard of the Facebook graph, which is you take yourself and all your friends and you draw a line between you and all your friends. And for example, with the Facebook graph, you can't really have an edge connecting yourself. That doesn't make much sense. You can't have multiple edges between you and somebody else. You're either friends or not. So this is a very good abstract framework with which to start thinking about how various entities are related to each other. Okay? So people who are particularly popular on Facebook, for example, or have groups that are particularly popular, are going to have a lot of edges coming out of them. And any message or any content that comes from that node is probably going to be disseminated much faster or much broader than other types of nodes. So this is a very fundamental way of thinking, which is very practical as well. Basically, I just took all the images from the Wikipedia page, and I'm just kind of wanting to give you a comprehensive background before we start applying it. Okay, so a directed graph is a graph where the vertices are connected by edges which are directional. So you could think of maybe like the flow of water. That's going to be one directional. But you could also think of it like relationships. Okay, you have a parent-child relationship that is directional. It is not reversible. Okay, so that's where the arrows usually have some meaning. You can also have them be double, have directions on both sides. That's fine as well. Okay, so in general, there's this idea of just like the Facebook graph, there's a bunch of nodes and they're either connected or not connected, or you can even put directions on them as well, which restricts the movement along the graph. Okay, so let me just double check here. Yeah, okay, so anything in black bold is, these are terms I'm going to use in the future that you need to know, but I'm not going to, on an exam, for example, ask you to define a directed graph. I'm not so keen on that for this class. This is about programming, but we need to know what these terms are in order for the other more complicated things to make sense. Okay, so the blue bold, those are the ones that could, appear on the exam as define what this means. And then you're free to use terms like directed graph as if they were synonymous. Okay? So we just need the terms in black. They're terms you may not have known before, but you definitely need to know them to understand the later concepts later on. So again, let's just make these intuitive notions clear so that when I talk about a path or a cycle or no cycles, it's not ambiguous. It's not an English language thing. This is a technical set of terms which have definitions. Okay? So a path, or more specifically a simple path, is just a sequence of vertices connected by edges with the starting point and ending point and no repeated vertices. Okay? So a path is like starting from here and going to there, or going from here and maybe going to there, but it doesn't double back on itself at all. Okay? That's a path. A simple cycle is a simple path where the starting point and ending points are the same. Okay? In other words, if I start here and I go along here, that in your mind, that should be synonymous with the idea of a cycle. And that's the technical term as well. Okay? Same thing with a path. Just keep in mind with a path, we're implying that you don't double back on the path. Okay? So these are very intuitive notions that I just want to make sure that I have them properly defined moving forward. And then from now on, everything we're going to think of is as simple. Okay? Everything is just very simple. Simple cycle, simple path, whenever you see those words. Okay? Now, a tree is a graph with no cycles. Okay? That's why I've defined the words tree and a graph and cycle. Okay? So you think of any graph you want, as long as and it's going to be simple. So forget about directional edges for the moment. Just edges there or not there. If there are no cycles, it's actually a tree. And you think about that for a minute. If you look at a tree and it grows and it branches out, do the branches ever connect back in with the trunk or any of the branches? What's that? Can you name them off the top of your head? There you go. Okay, so they don't exist. All right. Okay, yeah, there are several species where maybe they double back, but they're rare, right? You would agree that they're rare. And that our intuition about a tree is primarily one which doesn't double back, which is where the connection with the language comes from. But yes, that's a very good point. Just like in C++, everything I tell you is a lie, but it's a very good lie. I didn't coin that. The guy named Scott Myers coined that phrase. Okay? So same thing. With a tree, right, usually it doesn't double back, but there do exist some bizarre cases where it does. Okay? But in general, that intuition will guide you well. Okay? So then there's the idea of just a tree, which is literally just any collection of nodes and edges where there's no cycles. You cannot find a way to construct a path that ends up going back to the original node without having to double back on the path. Okay? Then there's the idea of a rooted tree, and a rooted tree is a tree where you take one node as being special. One node is sort of like the root by which all things emanate from. Okay? And you can switch up the root. So for these set of nodes, I can make the 8 the root, and then I would just be kind of like pulling it, and it would rearrange how those look, but all the connections would stay the same. Okay? Just how you look at and think of the tree might change a bit. Okay? So the root node is the node at the top of the tree. Okay? That's the idea of it. That's going to be important later on when we talk about binary search trees, and in particular heaps. The root node, or is it root or root? What is it? Root? Okay, sometimes I wonder if that's a Minnesotan thing. Root versus root. Does anyone ever call it root? Is it very Minnesotan? Okay. Missouri too? Okay. Any other M states that this happens? Okay. All right, so however you pronounce it, that's how it's spelled. And it does have a very specific special role. Now, a binary tree. This is a term that, yes, I could actually absolutely put on an exam and say, explain what is a binary tree. Okay? So, it is a rooted tree. So again, we need those terms, the rooted tree, where each node has at most 2 children, which we shall call the left and right nodes. Okay, period. Binary tree. Binary tree is really just a node that has at most 2 children, a left and a right. That's why it's called binary. Okay? You either have no children, 1 child, or 2 children. Okay? Oh, and I guess there's a definition for child and descendants and on the next slide. So it's what you think it is. So this 4 is a child of that 9. And that 9 is the parent of that 4. Think of how a family tree works. Okay? Now, a binary search tree, not just binary tree, but a binary search tree is a binary tree that satisfies 2 additional structural properties. Okay? This is what makes the binary search tree a very nice structure to work with on occasion. 1, the data values of all descendants to the left. So by descendants, what it means is all children on the left and the children of that node, any left or right children of that node. But any children on the left, so the descendants to the left is the 7, the 2, the 6, the 5, and the 11. Everything to the left of the 2. Those are its left descendants. These have to be less than the data value stored in that node. So you take the 2, and everything to the left of the 2 has to be less than the 2. Similarly, all descendants to the right of the 2 would have to be larger than the 2. Okay? That's what makes a binary tree a binary search tree. Okay? So each node in a binary tree has a parent node, except the root node. The root node has no parent node. Okay? But each node has a parent node. It's just the node that's just above it it's being pointed at. Okay? And then the parent has its parent node. And you could call that the grandfather node or grandmother node. It doesn't really matter. But what does matter is that you pick a term like ancestor nodes or predecessors nodes. Okay? So ancestor nodes is usually a little bit more formal. Okay? So it has its ancestors, which are the nodes strictly above. But the 1 and the 6, the 1 is not an ancestor of the 6. They're just sort of side by side. Okay? Whereas the 8 is an ancestor to all of the nodes in the tree. The children nodes are the 0, 1, or 2 nodes that it points to on the left and the right. So again, it's just that family tree kind of structure. And the children nodes and their children's nodes, etc., are called the descendants. And again, think family tree, and all these terms should just be very natural. Okay. This one is my own concoction. When I did the lectures on binary and how numbers are stored in the computer, this one was really kind of a nice one to throw in there. But let's think about it anyway. Each node also has a binary representation. Okay, so this is kind of something you can place on the nodes. You don't have to, but you could. So the node 6 is represented as 0, 1. Okay, so in other words, you go to the left and then you go to the right. So 0 means go to the left from the root, and 1 means go to the right. And we're assuming the root node has representation, the empty thing. Okay, so it's arbitrary how I've created this code, but it's just to get you to think a little bit more in binary, because that's the language of computers. So you could look at the node 13 as to the right, to the right, to the left as 1, 1, 0, for example. Okay. The reason why this is kind of a cool construct is that binary code is unique for each node in the tree. So each node can be uniquely identified based on a series of left and right moves. Okay? That's why the idea is kind of neat. It's also neat in practice as well. Do you guys ever go to like Brookstone or one of those stores and there's like a game called 20 Questions? You guys ever see this game? You take up this unit and it says like person or place or thing or something, and you say 2 for person or something. Or person or place. Person. Movie star or something. And you just pick characteristics. And after about 4 or 5 questions, it either takes a guess and it's correct, or it doesn't, and you try and trick it or something. Okay, but it's usually quite accurate. Okay, it's usually pretty good. And the reason is because of the idea of a binary search tree. Every time you make a yes or no decision, you basically include twice as many possibilities as before. So after one question, you can disambiguate between two items or two ideas. After 2 questions, you go down 2 levels. You have like a no, 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 yes, yes, no, yes, yes. You have 4. So if you go down 20 levels, for example, that's 2 to the 20th different items on that last row. What is 2 to the 20th, approximately? A what? Gajillion. A gajillion. Is that a technical term? No, but it's actually closer to replace the g with a m. Wait, no. No, sorry. It's about 1 million. It's about 1 million. Yeah, okay? So when you think about it, in your brain, can you really think, if I were to have you sit down and write out all the different things that could possibly be on your mind, all the words you could think of, all the things you could think of, do you think you could really specify more than 1 million things? No. Your vocabulary is in the tens of thousands. Shakespeare's was about double of what our vocabulary was. And even his was like 50 or 60,000, I remember reading once. Okay? So this 20 questions can conceivably pretty much pick out almost all of the usual things that you would be thinking of on a daily basis. That's why it can be so good. You know, the answer, don't worry about that for now. You don't need to know that. If there's time later, I'll explain what I mean by that. Okay. Well, okay, so maybe I will describe it. Okay, so the answer is something like 2 to the 20th or 2 to the 21st minus 1, something like that. In previous years, when I do the binary integers, I teach them this really cool thing, which is 2 to the 10th. Do you know what 2 to the 10th is exactly? 1024, right? 2 to the 10th is 1024. That's approximately what? 1,000. Let me show you this cute little calculation real quick. Because I remember learning this and thinking, hey, I like this. I can use this in the future. Okay, so 2 to the 10th is equal to 1024, and that's approximately 1,000. Okay? Now, 2 to the 20th is, now what you do is you just rewrite 2 to the whatever in terms of 2 to the 10th with something else. So for example, here you'd write it as 2 to the 10th squared. This inside is approximately what? 10 cubed. And then you square it, and that's approximately what? Or that's, well, this is the approximation, and then this is equal to 10 to the 6th. Okay? So whenever you see a power of 2, like 2 to the 50th, don't kind of freeze up or think, oh, I have to take out a calculator. Well, if you just need an approximate answer, well, what is 2 to the 50th? 2 to the 50th. Let's do 2 to the 53rd. How could you write this? So first, let's pull out 3 factors of 2 so that we get a perfect division of 10 there. And then we write it as an exponent. So 2 cubed is 8. And then we get 2 to the 10th to the 5. And then this is approximately equal to 8 times 10 cubed to the 5th. Or in other words, 8 times 10 to the 15th. Okay? So powers of 2, wherever you see them, you can easily convert them to powers of 10. Okay? And we think more naturally in powers of 10. Okay? So with 20 questions, 2 to the 20th is approximately equal to something like 10 to the 6th. So if we appeal to big O, that's a bad idea here. Don't worry about that. Okay. So anyway, usually this approximation is 2 million or 1 million. Usually it's about the million that we care mostly about. Okay. So here we have 8 times 10 to the 15th. So you could even write this as, and this is what we often do, we often write this as approximately 10 to the 16th. Okay? So 8 is pretty close to 10. We're doing approximations anyway. Why not? Okay? So that's how to easily convert from powers of 2 to powers of 10. All right. So in a binary search tree with 20 levels, that gives us about 1 million or 2 million or so different possibilities. So what would a binary search tree class look like? Okay? So first of all, we need a tree node. We need a node class to store the data. This is going to be similar to the linked list node, except, remember, with the linked list node, we had 2 pointers, one pointing to the left and one pointing to the right. Here we have the same thing, except they're pointing to left children or to the left child or the right child. And there may be, the right pointer might actually be null, right? If you don't have any right children, you may not have any pointers going that way. Okay? So in general, you have a left and a right pointer, and then you have this string data. You have this something you're storing in the node, whether it's an int or a string or a double, it doesn't really matter. It's the same idea. Okay? And then what are some things you might want to do with that node? You might need to insert a node that's connected to that node. You might need to, try and find a node, et cetera, et cetera. These are really more just helper functions for other ones that are going to be in the binary search tree class. Okay? So the tree node, just focus for now on, you have the data, and then you have the left and right children that it points to. And then the binary search tree class itself, okay, the binary search tree class is, this is the one that kind of runs the show. All right? So this runs the show. You're going to create a binary search tree object. You're going to call insert on that object. You're not actually going to create any tree nodes yourself. The insert function is going to create a node initialized with the data that you give to it. Okay? It's kind of like the set container. If you want to create a set of ints, you call insert with the value of 5, for example, and it will create an internal version of a node, store the value 5 in that node, but you don't have to know anything about how the data is actually being stored. Okay? Similarly, if we want to count the number of elements in the binary search tree, either in this case it's just a 0 or a 1. We're not going to allow duplicates. And then you also want to be able to erase a node as well. And then print. Print is a nice one. Okay? All right. So now, each node in a linked list, like I said, has 2 node pointers, one to the previous and one to the next. Similarly, the binary search tree also has 2 tree node pointers, but they go downward rather than left-right. Okay? And in fact, a binary search tree is really more like a singly linked list in the sense that it really is one directional. Okay? Yeah. You go in one direction down the chain, and you don't, in the way I've set it up here, you don't actually have the ability to go back up. All right, now this is where the fun set of slides begins. Okay, so like I said, you have a binary search tree, and you call insert on, say, the 9. And you've previously inserted those elements right there. Okay? How does it put the 9 in its proper place? Where is the 9's proper place? Okay. So first, is there a unique place where we can put the 9, or do we have a choice? And if it's unique, where is that position? So where do you suppose the 9 goes in this? Say it loud. To the left of the 10. Yeah, so the idea of before 10, right, we know what you're saying, but we want to emphasize to the left as the left child of the 10. Okay? So it is the left child of the 10. Is there any other place that the 9 could go? No. The choice is unique, okay? Why is it unique? Well, we're not going to prove that it's unique, but let's just think about why it's unique. You go to the 8. Again, we're assuming all these numbers are different. We're not assuming there's duplicates, so everything's different, okay? You look at the 8, and what does the 9 have to do? It has to decide between going, left or right. Can it go left? No, it has no choice. It must go to the right. Now it gets to the 10. Does it have any choice? Has to go left. Now there's nowhere else it can go. There's no other nodes there to look. That's where it stays. So in your mind, or in my mind anyway, I see this picture. I go, here, 9's bigger than 8. I go there. 9's less than 10. I join the the 10. I joined the 10's family. Okay, here's the code to do it. Now let's relax. Okay, we'll get through this. Okay, here we go. So this is this is the binary search tree member function insert. Okay, this is insert for the binary search tree. So your binary search tree object calls like b.insert of Bob. Okay, so Bob is the string. So what does it do? It first creates a new node called tree node. It initializes the value of the data. Okay. Now, the reason it can access the private member variables is because we added that friend declaration in the tree node class. Okay. So it can access the tree node private data members just fine. Okay. Now, wherever we insert the node, it's always going to be where? At the end of the tree. Okay? We're not going to stop midway and say, oh, let's take the 9 and let's kick out the 10 and bump the 10 down further. The process for insertion always compares until there's a free node to the left or to the right where appropriate. Okay? And then it adds in the node and the link as the child. Okay? You can restructure a binary search tree, that's fine. But for inserting purposes, you're going to keep going until you're down at the bottom at one of these branches. Okay? So we're going to initialize the left and right pointers to be null PTR. Not NULL, that's the old way of doing things. NULL PTR all lowercase. That's a C++11 keyword. Okay? So what is the first thing we do? We check to see if there is no root. Right? If initially the root pointer is set to null PTR, that means there's no nodes in our tree. So if there are no nodes in our tree, then we set root equal to this new node, and then we're basically done. We say we've inserted, now we have a root, we're done. If there is a root node already, then we know that we have some kind of tree structure, and what we want to do now is we want to start a recursive chain reaction. Okay? So we're going to utilize recursion now in storing or in searching for the 9's proper place. Okay? So the root node then calls not insert, but the tree node member function called insert node, using the node itself, not the data, but the new node object itself, the tree node pointer type. Okay? You can do it other ways, but just keep in mind that we're inside the insert function for binary search tree. Now what we're doing is we're then calling the insert node function, which is a member function of a tree node of the tree node class. Then the tree node function insert node, it accepts a tree node pointer, and then it checks to see, does the new competing node, does the 9, for example, is its data less than the 8? Right? Because right now we're in the root. The root node is calling this insert node function, so its data is 8. And our new node is, say, a 9. And we check, is 9 less than 8? That's false. So we go to the else. If new node data is greater than data, that's true, the 9 is greater than the 8. Then what we do is we check. If 8's right child is null, we become the right child. If the right child is not null, then what do? We do the exact same thing, just now using the 10. And this is not exactly recursive because we're technically calling a different insert node. We're calling the same set of instructions, but the node calling it is different than the node in the previous function call. Okay? So here the 8 node is calling this function. Here what we're saying is, well, when you're done with this, before you finish off the 8 node, go to the 10 node, and the 10 node is going to call its own version of insert node. And then when we go into the 10, we start from the top, and we ask, okay, well, is the 9 less than the 10? And the answer is yes. Okay? New node data, which is 9, less than data, which is now 10. Then does the 10 have a left child? The answer is no. The left child is, its left pointer is null PTR. And so we set left equal to that new node. We found its home. We exit out of that function. The 10 exits out of its function. The 8 exits out of its function. And we're done. We've inserted the node. Okay. That was the easy part. Inserting a node is the easy part. Yeah, question? Yeah, so the comment is that you could have the same idea of ordering left to right, the same set of comparisons, but the order in which you insert the elements absolutely does matter. If you insert a 1, then a 2, then a 3, then a 4, then a 5, then a 6, you get a very long, nice chain, which kind of defeats the whole purpose of having this structure. Yes, so that is an issue that comes up, and there's a solution called rebalancing a tree. We're not going to cover that. We assume if you're using a good binary search tree library, it'll have that built in. There's another related data structure called a heap, which we'll cover either next time or the time after, which does maintain what's called balance in the tree. So yeah, the order in which you insert the elements can have a dramatic impact on the shape of the tree. How about erasing? Erasing is just messy. It's not intellectually or intuitively complicated. It's really quite simple. But coding it up is actually a nightmare. Why is it a nightmare? It's a nightmare because you're messing with pointers. Okay? There's a reason why in the more recent years, programming in C and C++ has converged to a more sort of thinking in terms of objects rather than pointers. Whenever you start playing around with pointers, you're playing with fire. Okay? You mess up one little thing. You just, what's that over there? Oh, now you have 5 bugs in your code. Okay? So pointers are incredibly tedious to work with. There is no partial credit. Either it works completely and it does what it's supposed to, or it's going to crash eventually through use. So that's why the emphasis has been less and less on pointers and more on sort of thinking in terms of objects and moving and copying and things like that. Okay? But you got to learn it once. You got to implement it once, understand how horrible it is so you can appreciate the other side. Okay? So that, and for your homework assignment, you are going to probably hate me, but it's a necessary part of understanding the binary search tree structure and then appreciating that you don't have to really implement it yourself most of the time. Okay? But you do got to do it at least once to get a feel for it. Otherwise you don't really get it. Okay, so how do you erase a node? There are basically a bunch of different cases. If the node is not in the tree, you're done. You've erased it. Okay? It's like set minus. If you try and set minus something that's not in the set, it's just the set. Don't worry about it. Okay, now, you could have a node like the 4. That has no children. How would you erase this node 4? Okay, so if you read the book, it'll tell you to set the 6's left pointer to null PTR. And then the 4 just no longer is part of the tree anymore. But who created the 4? Who created the node 4? The binary search tree class. Does anything else link to this node anymore? The only thing that links to this node is the left pointer of the 6. So if you just set the left node pointer of the 6 to null, what do you get? Memory leak. Shame on you, book. Okay. All right. So you can do it, and when your program finishes running, all that memory will get cleaned up. That's not a big, big deal. But if you're writing software to run on a server, for example, that's a big no-no. Okay? So just in general, you don't want memory leaks. I think I know why your book has a memory leak in this case, but I'm not 100% certain, so I won't comment. But for the homework, you're going to fix the memory leaks. Okay? For your homework, you're going to actually implement a binary search tree with some variations. You can start with the code from the book, but you're going to do a little bit better memory management than what the book currently does. Okay? So if there's no children, you call delete on the 4, and then you set the left pointer to null. Okay? Then you're good. All right? That's how you fix the memory leak. It's not that complicated. Okay. Now, if it has one child, it's easier to think about, but let's do it in pictures, okay? So let's think about, I think it's in the next few slides. Yeah, memory leak, the book says, if the node to be removed simply has no children at all, then the parent link is simply set to null. Yeah, okay, that's going to get you your memory leak, okay? So you're not going to get any errors, you're not going to get anything complaining at you, yelling at you, it's just a leak, and that is egregious. You don't code that way. Okay. Basically, this is what's following the RAII principle. Binary search tree, when you call insert, remember the insert function. In the insert function for binary search tree, you bring the node into existence on the heap. If you bring the node into existence within the class, you are responsible for deallocating it, for calling delete on it. Okay? That's why your book has that memory leak, because you have to call delete somewhere in it. I think the reason it doesn't have the delete there is because in general, you also need a destructor for this. And it doesn't teach destructors until chapter 15. Okay, that's my guess. But yeah, you definitely need a destructor at the end to free up all those nodes. Okay, so let's say we want to remove the 3. First, we have to find the 3. Oh, now I get, okay. Anyway, okay, let's just do it this way. All right, so we want to remove the 3. Here's one way to do it. Okay, so we find the 3. Then we look at the subtrees. And the idea is not to just replace it with the 1 or the 6. This is very important, okay? You replace its data value with the closest data value in one of the subtrees of its descendants. You pick a left or a right subtree, and you say I picked the right subtree. I want to find in that right subtree the value closest to 3. What value is that? The 4. Okay? So what is the idea? The idea is you pick a left or a right, say it's left, and then you pull all the way to the right as possible, and you take that value. And in this case, it's the 1. Or you pick the right subtree, and you say, I go first to the 6, I go to the right, and then I pull as far to the left as I possibly can before there's no more left children. And that's where you get the 4. And the 4 is what you want to replace the 3 with. Why do we want to do that? Okay? So we look at the 3. Let's say we go to the right. Then we pull as far to the left as possible. Then we replace the 4. Okay? We replace the 3 with the 4. Now, why is this a good idea? Do I have to worry about the nodes to the left of the 4? Of the new 4? No, because anything on the right subtree is always going to be larger than anything on that left subtree. So even the smallest element on the right is still going to be larger than everything on the left. So that stays put. What about the elements on the right? Am I upsetting the balance by moving the 4 up there? No, why? Because it's the smallest element on the right. And if it's the smallest element on the right, it's smaller than everything to the right. Okay? So by moving the 4 up there, everything else stays the same, What is the last little thing I just need to do to make sure I clean up after myself? Deallocate the old 4. Done. Okay, so let's see that again. So you go to the 3, you pick a left or a right subtree. Let's say you go to the right, then you pull all the way to the left. You replace that node with that value, and then you just get rid of that old node's location. And everything is still ordered the way it needs to be. Okay, so that's when the 4 has no children. Okay, what if the 4 now has a right child, which is a 5, right? So here we want to remove the 3. We go to the right subtree, we pull all the way to the left, and now we want to replace the 4 with the 3. But we can't just delete this node and then set left equal to null. We have to worry about the 5. But in this case, it's actually not a big deal because you just bypass the node. Okay? Anything that was a descendant of the 4 is also going to be a descendant of the, well, anything that was a descendant of the 4 is going to be less than any of its ancestors. Okay? So, or it's the most immediate ancestor because it was a left node. Okay? Not any of its ancestors. Sorry, that was not correct. Okay. Its immediate ancestor, because we kept pulling to the left, its immediate ancestor is to the right of it, so it's larger. Okay? So anything that's a child of the 4 is less than that parent node. So we can just, if the 4 just has one element, then we just reroute it to the 5. Again, we reroute it, but we delete the old node before we just do the rerouting. Okay? Again, the book simply redirects the node with a 6 to point to the node with the 5. It's a memory leak. You got to delete the nodes as well. Yeah, do worry about the memory leak for now. I changed that. Yeah, I'm going to get rid of that. Don't worry about it. Do. Oh, wait, what did I do? Delete. Do worry about that. Okay. So here's the issue that, yeah, question.
Would you say like you use the erase function recursively? So you erase the 4, you erase the 3 up there, and you erase the 4.
Yes. So you could recursively do this. Rather than manually patching it up, you could recursively do it. Yeah. You either recursively do it and the code looks a bit nicer. So the real answer is you wouldn't actually do it this way. But I probably shouldn't have said that either. Because really you wouldn't overwrite individual values. You would have to redirect all the edges. Like the nodes themselves will be const. Once you create a node with a value of say like a 5, you actually don't want to be able to even modify it. Because let's say you change this 9 to a 12. Well, what would you have to do? You have to restructure the whole tree, right? So you don't want to be able to modify the contents themselves. You would want to force them to erase and then reinsert, for example. So here I'm cheating a little bit because I'm letting you overwrite the 3 here. But yeah, so the bottom line is, yeah, you could do it recursively, call delete again. Or you could just, again, call delete, and then it's not going to have a left child here because it was by default the most left child. So there's just one step here to link it. So one line of code, a recursive call versus maybe a delete and a reroute. The delete and reroute is going to be more efficient, but the recursive call might be easier to conceptualize. So that's the trade-off. Either one is fine for this class. In general, you would prefer the non-recursive solution. But for this class, that's fine either way. Okay. Okay, so we're almost done. So again, if we're not careful, we can get a pretty large and inefficient tree. If we add in the numbers 1, 2, 3, 4, 5, 6 in order, we get that. That's not ideal. On the other hand, if we inserted them in 3, 2, 1, 5, 4, 6, then we do get the kind of structure that we want. Okay? And now the reason that this is important is because of the following. First, a tree is called balanced. It's in blue and bold, so that's a term I could ask you to define and definitely expect you to know. If each node has approximately as many descendants on the left as on the right. What do I mean by approximate? 60%, 40%, you know it when you see it. You know an unbalanced tree when you see it. And then there's some gray area. Do you mean like 30-70? That would be a little unbalanced. Do you mean 40-60? That's probably, good enough. 45-55? There's really no definition for what it, balanced is when you have exactly this percentage on left. It's just a very intuitive notion of the trade-offs between letting the user input more nodes and then reshuffling them around afterwards. Okay? So, but balanced is the intuitive notion of what it would mean for a tree to have roughly the same amount of descendants on the left as on the right. Oh, I guess that's next time. Okay. Yeah, so next time we'll do lecture 21. We'll go through lecture 21.